Hey folks, I have an example for you regarding 2D motion using unit vectors. The givens on the left, I have let's say it's a ball on a table, but the table's tilted in both the x and the y direction, so the ball's going to accelerate with a constant acceleration. So on the left, I got vx naught and vy naught, the starting velocity of the ball. When we start our watch at 0 seconds, that's the velocity of the ball. We have the initial positions of the ball, and then we have the acceleration of the ball. And the acceleration is written in unit vector notation. And for this problem, we can assume that everything is meters and seconds. So like the acceleration would be 3 I hat minus 2J hat meters per second per second. There's three things we're going to determine. First, what's the average velocity between 0 and 3 seconds? The second thing is when is it at a position of 42 meters? And then finally, when and where does it turn in the x and y direction? We're only going to look at positive time, so after you've started your watch. If you need a moment, go ahead and copy all the information down, and then we'll get going. All righty. So in order to do this problem, there's a lot of ways that we can do this. What I'm going to do is I'm going to write the position and the velocity of this object as functions of time in unit vector notation. And so I'll start with the position vector. So that's r, okay, as a function of time. And this is a constant acceleration problem. The acceleration does not vary. So I'm allowed to use my constant accelerations equation. So for position, I'm going to write this up above here. I'm going to write x naught plus v naught t plus 1/2 a t squared. And I'm just going to do that for both the x and the y direction. So in the x direction, and I'm going to use parentheses to kind of denote this, x naught is 5. V naught in the x direction is 10, so I got a 10t plus 1/2 a. A in the x direction is 3, so half of that is 1.5 t squared. So that's our I hat position at any moment. And we're going to do the exact same thing in the y direction for our j hat position. Y naught is 8. Vy naught is 6, so I got a 6t plus 1/2 at squared. A is -2, so I'm going to actually make, instead of a plus here, I'm going to put a minus. 1/2 of 2 is 1, so 1t squared, and that's j hat. So that is the position of the object as a function of time, and if I put any time in there I want, I can map out exactly where the object's at. For velocity as a function of time, you have several options here. The option I'm going to choose, though, is I know that velocity is dr dt, okay? That's the derivative of position, the time derivative of position. So I'm going to start with the x direction. The derivative of 5 is 0, so I'm not going to write that down. The derivative of 10t is simply 10, and the derivative of 1.5t squared is 3t. So that's in the I direction. In the j direction, the derivative of 8 is 0. The derivative of 6t is just 6 minus, and the derivative of 1t squared is 2t, and that's our j direction. And by the way, if I took the derivative of that again, I would get 3I hat minus 2j hat, which is our acceleration. So we don't need to do that. We've already got it. Okay. So the first question that they ask is, what is the average velocity between 0 and 3 seconds? So remember, your definition of average velocity is change in position as over time, delta r over t. So we have to find the position, okay, at 3 seconds. I'll do that first, okay. So that would be, if I plug in a 3 here, we get 5 plus 10 times 3 is 30, plus 9 times 1.5 is 13.5. That's I hat. And then plus, in the j hat, we got 8 plus 3 times 6 is 18 minus 3 squared is 9 j hat. And I'll tie that up a little bit. So the position at the 3 second mark is 35, 38, 48.5 I hat plus 17 j hat meters. Okay. The position at 0, well, we can either plug in 0 for our time, or you were given the initial positions. They were just 5 and 8, okay? And if you plug in 0 for time, you're going to get that. So we've got a 5 I hat plus an 8 j hat meters, okay? To do the average velocity, we're going to do delta r over t. So we're going to take the blue minus the green. That's final minus initial. So 48.5 minus 5 is 43.5 I hat. And then we have 17 minus 8, which is 9 j hat. And the time that elapses is 3 seconds. And we end up getting, let's see here, 14.5 I hat plus 3 j hat meters per second. So that is the average velocity of this object as it travels between 0 and 3 seconds, okay? The next question says, when is the object at 42 meters? And the x, when is x equal 42? So literally, all I'm going to do is take the x coordinate here versus as a function of time and set that equal to 42. So we've got 42 equals 5 plus 10t plus 1.5t squared. Okay, and now we're going to do real quick math. I got 1.5t squared plus 10t minus 37 would be 0. And I'm going to double everything. So we got 3t squared plus 20t minus 74 equals 0. And if I were to plug those in the quadratic equation, and I've already worked that out, you get 2 times. You get 2.65 seconds. You would also get a negative time, a negative 9.32 seconds. We really don't care about that because we want positive times after we start our watch. So your answer would be is at 42 meters in the x direction at 2.65 seconds. Okay. Now, the last question asks, when does it turn in the x and y direction? And we're only looking for positive time. So let's start with a turn in x. Okay. Well, when something's in the process of turning around, at the turnaround moment, its velocity is 0. So imagine you're walking east, and I tell you to turn around. Well, if you start walking west, at the moment you change direction, you weren't moving. Your velocity was 0. So what we got to do is we got to set the x equal to 0. So 0 is going to equal, and our x velocity is 10 plus 3t. Now, if you solve for t here, you get negative 10/3 seconds, or negative 3 1/3. Because we only want positive times, we would say that for a positive time, the object does not turn around the x direction. If you look at our position vector, both the term in front of both t and t squared are both positive, so it's never turning around in the x direction. The same goes for y, or the same idea in y. So we're going to see, when does it turn in the y direction? Okay, we're going to set vy equal to 0. And so we're going to say 0 equals, and you get the vy is 6 minus 2t. So 6 minus 2t. So here we do get a positive time. You get 3 seconds. So that's when it turns in the y direction. And now, what is the y coordinate at that? Well, the cool part is we already know that. Okay, we found the position vector. Okay, at 3 seconds. Okay, so I'm actually going to write that whole thing out here. So r at 3 seconds is, we already have the answer. It's 48.5 I plus 17j. So 48.5 I plus 17 j hat meters. So that is where it's at the moment it's turning around in the y direction. Its max y coordinate is 17. And that's because in the y part of this, the t squared term is negative. So eventually it's going to dominate everything else. So for a little while it goes forward because you have a positive 8 and a positive 6t, but eventually the negative 1t squared dominates and starts going backward, and that occurs at the 3 second mark. Well, I hope that example was helpful, and thank you very much.